Hello everyone, I'm Vikram Madduri here. I'm a software architect. Welcome to Softech. In this session, we are going to discuss about the machine learning chapter 1 part 3. What we have discussed in the previous sessions, the past two sessions is about the taste of machine learning, applications, data and the problems. Now in this session, we are going to discuss about the probability theory in which we are going to discuss in detail about the random variables, distribution, how the distribution happens, mean and variance, marginalization, independence, conditioning, and base rules. These are the things that we are going to discuss from the probability theory in this session. And later point of time in the coming sessions, we are going to discuss about the basic algorithms like naive Bayes, nearest neighbor estimators, a simple classifier, perceptron, and k-means. These are the things that we're going to discuss about the basic algorithms in the coming sessions. Now, from the probability theory, in order to deal with the instances of where machine learning can be used, in case like there is a particular example of a industrial level manufacturing where it has to be used, we need to develop an adequate language which is able to describe the problems concisely. So if at all, if we have to, what are the basic operations? What would happen if something doesn't go well? All these things have to be described carefully in that language. So below, we begin with a fairly informal overview over probability theory. For more details and a very gentle and detailed discussion, we'll see the further discussions. Now, in the probability, we'll first discuss about the random variables. Let's assume that we cast a dice, and let's say we a dice is a coin, and we would like to know our chances whether we would see one rather than another digit. If the dice is fair, all six outcomes, like for example, if the dice is having six, the probability of 1, 2, 3, 4, 5, 6, x is equals to 1, so on to 6, are equally likely to occur. Hence, we would see a 1 in roughly 1 out of 6 cases. The probability theory allows us to model uncertainty in the outcome of such experiments. Normally, we state that 1 occurs with probability of 1 out of 6. 1 of 6. In many experiments, such as the roll of a dice, outcomes are of a numerical nature and we can handle them easily. In some other cases, the outcomes may not be numerical. So let's take an example of it. If we toss a coin and observe heads or tails, in these cases, it is useful to associate numerical values to the outcomes. So this is done via a random variable. For instance, we can let a random variable. So let's say we'll take the x, take on a value +1 whenever the coin lands heads, and a value of -1 otherwise. It, that I mean to say it's tails. If it's tails -1, if it's heads +1. So our notational convention will be to use uppercase letters, example X, capital X or capital Y, etc., to denote random variables, and lowercase letters like small x, small y, etc., to denote the values they take. So in this way, so I repeat. So in this example, we have capital X and capital Y to denote the random variables, and lowercase letters to denote the values they take. Let's consider an example where we have a variable called sigma maps from the set of outcomes of an experiment denoted here by x. So here to real numbers, and this illustration here x consists of patients a physician might encounter, and they are mapped via sigma to their weight and height. This is one random example that we are actually taking, wherein we are considering a height and weight probability of a patient which the physician might encounter. In this distributions, perhaps the most important way to characterize a random variable is to associate probabilities with the values it can take. So, if the random variable is discrete, that is, it is in a finite number of values, then This assignment of probabilities is called probability mass function, or PMF for short. So what exactly is the finite numbers? In fact, like if we consider, if just like we have taken an example of a dice has the probability of getting a value from 1 to 6. There cannot be any a number above 6 that can happen in that scenario. And when we are considering a coin, tossing a coin, in that as well we have either we get heads or we get tails. It's one or two. Maybe if we consider as one or two, we will be having one or two. Or if we consider as plus one or minus one, that's the finite kind of a values that we're going to happen in all the probabilities. That's called the probability mass function. This happens in a finite number of values. Now, let's say if you have something like what could be the length the light years distance of a particular planet or a particular star from Earth. So we cannot tell it as a finite number. So the probabilities would be very high. So we are specifically talking about the finite number of values here, and for that we are considering PMF. PMF stands for probability mass function. So when we consider a probability mass function, must be by definition non-negative. So it be by definition non-negative and must sum to 1. For instance, if the coin is fair, that's heads or tails are equally likely, the random variable x described above takes on values of +1 and probably the -1 with probability 0.5. So the probability of getting heads is 0.5 and the probability of getting tails is 0.5. So that will be +1 and -1. This can be written as P or of x is equals to +1 is equals to 0.5 and P r of x is equals to -1 is equals to 0.5. The probability of +1 is 0.5. The probability of -1 is 0.5. I hope everyone is clear with this concept. So when there is no danger of confusion, we'll use the slightly informal notation of P of x. So what I'm writing here is the P of x is equals to P probability r of x is equals to x, and the small x denotes the number. In case of a continuous random variable, the assignment of probabilities results in a probability destination function and the destiny function for PDF. It's called probability destiny function. Probability destiny function for short. So with some abuse of terminology, but keeping in line with the convention, we will often use destiny for distribution instead of for probability destiny function. So in this like probability destiny function, where exactly we have the probabilities result in in various assignments. Okay, so we'll see in the diagrammatically we'll see the two distributions: the uniform distribution, the P of x is equals to 1, and then we have the otherwise. So let's see here the two common densities here. Left is the uniform distribution over the intervals like -1 or +1. Right, we have the normal distribution with zero mean and unit variance, and the Gaussian distribution, also called as normal distribution, that would be coming up to P of x is equals to 1 root of 2 pi sigma 2 and exponent minus of x minus mu 2 to sigma 2. So this is something which we have the probability for the Gaussian distribution, and this is called the normal distribution that we have. So close associated with the PDF is the indefinite integral over P. It is commonly referred to as the cumulative distribution function. So we come across a couple of things which I'll repeat with you again, but I once would like to tell you once again that This PMF denotes the probability mass function. Probability mass function is what we discussed. And then we have something called PDF, that is probability density function. Here we have the PMF, probability mass function. Here we have probability density function. And then we have something called CDF. It's called cumulative distribution function. It's commonly referred whenever there is a closely associated with a probability distribution function is the indefinite integral over P. It's called cumulative distribution function. So in the cumulative distribution function for a real valued random variable x with PDF P with associated cumulative distribution F is given by f of x0, that's equal to P r x less than or equal to x0 is equals to zx0 minus infinite dt of x. So cumulative distribution function of f of x0 allows us to perform range queries on P efficiently. For instance, by integral calculus, we obtain PR of a less than or equal to x less than or equal to b is equals to z p a dt of x is equals to f of b minus f of a. So the values of x0 for which f of x0 assumes a specific value such as 0.1 or 0.5 have a special name. They are called the quantiles of distribution P. They are called the quantiles of distribution P. The definition quantiles. So if we consider let x belongs to 0 and 1, then the value of x0 for which the probability of x less than x0 is less than or equal to q, and the probability of x greater than x0 and less than or equal to 1 minus q is the q quantile of the distribution P. This is something which if you don't get it in the first time, you can listen to again and I listen to it twice or thrice. I am sure you're going to get this. So I'm not going to repeat it now right now again, but this is something which we need to focus on more. It's a very important concept which I'm going to discuss further. Quantiles. So when we discuss about the quantiles, we are considering q, and we are considering the probability of it, and then we are discussing that. So moreover, value x0 associated with q is equals to 0.5 is called the median. So this quantiles of a distribution correspond to the area under the integral of the density of x, for which the integral takes on a pre-specified values. So illustrated are the 0.1, 0.5 and 0.9 quantiles of respectively. So here this is the 0.1, this we have the 0.5 and the 0.9 quantiles. So then we have something called mean and variance. This is also a very important concept when we're discussing about the machine learning. So a common question to ask about a random variable is what its expected value might be. For instance, when measuring the voltage of a device, you might ask what its typical value might be. When deciding whether administer a growth hormone to a child, a doctor might ask what a sensible range of height should be. So for those purposes, we need to define expectations and related quantities of the distributions. So we would be basically having some standards. So let's say we have a standard. So what would be in general? Let's say let's take into consideration another example of, let's say, what could be the most probable height of a common man. So we say something like 5 feet to 6 feet. So that would be the mean and variance. So it would be the common range, but the person's height can even vary from say 3 feet or something like extremely a unique person, the smallest person in the world might also measure something like 1 or 2 feet. So maybe it might be possible. So if we take the most extreme